If you are ever lucky enough to visit a glacier, listen carefully and you will hear a very characteristic sound. As the ice moves downhill under the weight of gravity, it comes under incredible strain. For bigger glaciers, this means millions of tons of solid ice must squeeze in and around the rocky valley walls surrounding it. You can actually hear the sound of ice structurally deforming, the creaking and groaning as it compresses, expands, or shears through time. Just like with ice, all materials have a characteristic pattern of accommodating strain through time. It's just not so easy to see or hear. Understanding these patterns of behavior in materials, however, allows us to make stronger and more reliable structures. Let me explain. This is ASU. Perhaps no other concepts are as central to solid mechanics as stress and strain. A few years ago, I was talking to a mechanical engineering student who told me that school was really stressing him out by stretching him thin. As any professor worth their ivory tower basement office would do, I pointed out that surely he meant that school was straining him by stretching him thin. Suffice to say, the student never returned to me for counsel again. Let's define strain. Consider a piece of chewing gum. If you now took the gum out of your mouth and held it in your hands, it has the shape of chewed gum. But let's say this piece of gum measures 10 centimeters. Now stretch this piece out to a total length of 20 centimeters. Congratulations! You have just applied a strain of 100% to the piece of gum you first spat out by stretching it an additional 10 centimeters. So what does this mean for our definition? Strain is the relative change in size caused by deformation. And the key word here is relative. Relative to its original size. Let's take our 20 centimeter piece of gum again. Now, stretch it by another 10 centimeters to a new total length of 30 centimeters. You've stretched it by the same amount, but the strain is now only 50% instead of 100%. Why? Because relative to the original size, you've stretched it only half as much. So that was strain. What about strain rate? Strain rate is nothing but the amount of strain per unit time. So strain rate is to strain what speed is to distance. Strain itself tells us nothing about how fast you stretch the gum. It only tells us how much you did. But why does it matter how fast or slow we stretch something? It matters because materials and structures respond differently depending on how fast they are stretched. Generally speaking, the faster you strain a material, the harder it resists that strain. And this is particularly true for plastics, as well as for metals at high temperatures, essentially for materials that demonstrate flow-like behavior. The material tends to get stiffer and fails at higher loads. If you apply very high strain rates, the material may even stop flowing and experience brittle fracture. Engineers conduct experiments on materials by stretching them at different strain rates and obtain data that is then used to develop models that predict how, for example, a solder joint in a laptop will behave under both repeated heating and cooling as it is turned off and on several times a day, and under the odd impact when its user drops it to the floor a couple of times a year, say. The former, the slow expansion and contraction under thermal differences, is a low strain event. The latter, the floor drop, is a high-strain event, and solder materials must be selected to withstand both. The student I began my story with has now graduated and is an engineer designing rockets in a high-paced industry. In addition, he and his partner just had their first baby, a stressful time by any measure. I met him recently at a conference and asked him how he was juggling the new job and the new baby. He seemed to have remembered our conversation, since he simply said, "Life will strain you in different amounts and at different rates. Your job is to recognize these differences and respond proportionally. You just cannot teach that." So if you do ever visit a glacier, remember to listen carefully. You might just hear the sounds of strain playing out around you. It happens in all materials. Even though we cannot always hear it, it is taking place. By understanding strain and its rates and their implications, we can build bigger, stronger, and safer structures at whatever scale we choose. This was ASU. Thanks for watching.